Okay, grade 12, we're almost finished. Just a couple more lessons left for topic 12, and we're officially done. So, after learning about Rutherford's experiment and the physics of the nucleus, we got a few more topics to talk about where we're going to unsolve some of these mysteries of the nucleus that came out, that all inside that nucleus isn't what meets the eye. Okay, so first of all, the nucleus, just like the electrons that are orbiting atom, have energy levels. And how do we discover that? Well, we looked at decay pathways of radiation. So, for example, here is a alpha decay of plutonium. When we looked at the kinetic energies of the alpha particles coming off, right, we can calculate what that kinetic energy can be using the mass defect on paper. We should be able to calculate exactly what that alpha particle decay should be and how much energy it should have. But when we measured the kinetic energy in the lab using particle accelerators or cloud chambers and magnetic fields to measure deflection of alpha particles, we would find that alpha particles came off with various energies, but the energy wasn't random, the energy was discrete. So let's take a look at what would happen here. If a plutonium atom, which has that energy state, undergoes decay, it'll emit an alpha particle. And when that alpha particle emits, it creates a nucleus that has some gaps in it. It's an excited state nucleus. And that nucleus is then going to collapse to a lower energy state, this ground state. And when it does that, it emits energy of its own, and that energy corresponds to photons or gamma rays, okay? And this alpha particle will shoot off with certain kinetic energies. But the way this diagram is drawn, that alpha particle has very discrete energy. It should have a very specific energy, and I should only be getting one gamma photon coming off with that discrete energy. In reality, what I'm about to show you is that there are multiple excited states. Okay, so this alpha particle can go to different excited states, and then if it does that, the gamma ray emitted will have different energies. So we will have discrete energies of alpha particles coming off, and you're going to have discrete energies of ultimate gamma rays coming off due to the relaxation of that nucleus. And lo and behold, we see that. So I've stolen this from a different presentation I found online, and you can see here's a alpha decay of a bismuth atom that is starting at that energy level. Okay, and when it decays into a thallium nucleus, but that thallium nucleus has multiple energy states. Okay, and that nucleus can relax from different excited states to its ground state at the bottom. So these alpha particle relaxations would all have different energy levels. We can calculate their kinetic energy by looking at the difference in energy from that level to that level, or that level to that level. And that would tell me about the kinetic energy that would be released for that alpha particle. Okay, and then the corresponding wavelengths of the photons I can use, just like we've done before with the electron volts, converting that into joules and then calculating the wavelength using this formula. You can calculate the wavelength of those gamma rays that come off. So very rare, but that could appear as a question on the IB exam where you have to calculate the energy of alpha particles or calculate the energy of the gamma rays or the wavelength of those gamma rays. I think that would be far-fetched, but you should know that the fact that alpha particles come off with multiple discrete energy levels and gamma rays come off with discrete energy levels is evidence that the nucleus also has energy levels, like electrons that orbit an atom have energy levels. So there's a lot more that meets the eye, especially if you went back and read topic 7.3 and we talked about the standard model with all that particle zoo that exists when we smash nucleus together. There's a lot for you guys, if you want to stay in physics, to learn about the magic that is within the nucleus. As we unravel more and more mysteries, we start to see that, wow, the physics within there there's just so much we don't know. All right, so the rest of this presentation is a what happens if. Okay, so this is going back and touching on a few things. What happens if matter meets antimatter? In topic 7.3, you guys have been reading this about matter and antimatter. Okay, quarks, leptons, and then the anti-quarks and anti-leptons. All right, what happens if matter meets antimatter? Well, this happens all the time. Matter and antimatter exist on our planet. Okay, for an example, what happens if an electron meets a positron? Okay, we use positrons in medicine, so they exist. What happens if an electron traveling in one direction meets a positron traveling in the opposite direction? Well, what will happen is they will annihilate each other. They will then be converted into two photons. Okay, and in that conversion, their kinetic energies will add up, and the two photons that are going to be emitted is the energy of those photons will equal to the kinetic energy plus the rest mass, because their mass is being converted into energy. So matter will be converted to energy. If I know their mass, I can convert that mass into energy using E equals mc squared, and I'll be able to then calculate the energy of these two photons that will go in opposite directions to conserve that energy of that collision. Okay, so matter will spontaneously be converted into energy, and if that's true, then we should get the opposite, where energy or light can be converted into matter. Okay, and in topic 7.3, you would see that if we smash nuclei, they would turn into energy, and that energy would come back and distill back into matter using this process. In order for that to happen, a photon that appears has to interact with a nucleus so that they can form a pair and conserve their momentum. And when they interact, they will form, that photon will be converted, it'll form into two matter particles, an antimatter particle and a matter particle. So in these Feynman diagrams, we're seeing that antimatter goes against time, it goes in the opposite direction, and matter, and the arrow goes with time. So that's how I can distinguish between which arrow is antimatter and which arrow is matter at that crossing point. Okay, and so the energy in that photon will be converted into matter. Okay, and then I can figure out the kinetic energy of those particles coming off if I know the energy of that photon. And that's called pair production. So pair annihilation is when matter is converted into light. Pair production is when light energy is converted into matter. Okay, and the last what happens if is when we're learning in astrophysics, you guys just learned right now, all of a sudden in a star, if it gets, the gravity's intense, electrons will be sucked into a proton, will sucked into a nucleus. Okay, and I think that was happening in the core of a star that is degrading and compressing. And if we get these interactions where an electron falls into a proton, electron capture, what will end up happening is that proton will be converted into a neutron, and to conserve lepton number, another particle has to be emitted, and that is the neutrino. The neutrino is a hot topic right now in physics. It's won a lot of it's won a lot of Nobel Prizes in the past 10 years or so. Very difficult particle to discover because it's neutral. It's hard to discover neutral, especially small and extremely fast-moving particles, but now we're able to detect them, and the physics behind them are very fascinating. And as you would have learned in topic 7.3, neutrinos are always associated with electrons. An electron has a neutrino pair. Okay, so you should have learned about that already. And now how did we actually provide evidence for neutrinos? Well, before we discovered them and actually devised experiments to find them, they were hypothesized on paper by a guy named Pauli. When we were looking at beta decays, when a neutron spontaneously becomes a proton and an electron in beta decay, if I do the math and look at the mass defect over here and try to calculate the energy of that electron that comes off, when I actually try to detect that energy of the electron comes off, something fishy occurs. Okay, we would see, using that E equals mc squared, I'd be able to calculate the energy of that electron. We would see not a single energy, we would see a distribution of energies of electrons coming off. And the average of that electron energy that comes off is actually less than it should be. It's always less than it should be. So there's missing energy. And what Pauli suggested was, well, if that missing energy is there, well, that energy should be associated with mass. So there must be a missing particle. So for years and years and years, the data behind a beta decay and the missing energy associated with that beta decay suggested that there must be some invisible particle that we don't know yet, and they called it the neutrino because it wasn't showing up in electric and magnetic fields. So because of that, they were able to hypothesize, and eventually we were able to devise experiments to find those neutrinos. So that missing energy is due to an additional particle called a neutrino. Now be careful, when we do this reaction, it's not a neutrino that is produced it is an antineutrino. And what you would have learned in topic 7.3 is the reason for why it's an antineutrino is because of conservation laws. Okay, the lepton number for an electron is positive. There are no leptons on this side, so I have to remove for conservation, the sum of the lepton numbers should be 0 on both sides. So that's why we have an antineutrino over here, because its lepton number would be negative. And you add those together, and that would be 0. And that's it.